Hello everybody, let's start lecture 37 and the course is corrosion protection methods. So we have been discussing change in electrode potential and associated corrosion protection. We have talked about mechanism, we have understood both the protection methods like cathodic as well as anodic protections with the help of mixed potential theory. And then we also talked about differences between ICCP as well as sacrificial anodes. Those are part of cathodic protection. Also, we have talked about the differences between anodic protection and cathodic protection. Now, we also tried to understand those differences in greater details also, like in case of anodic polarization. Initially, though, it requires very high current density, but later on, it actually goes to a very low current requirement to maintain protection potential. And it's a direct measure of corrosion rate, what we achieve during the protection. Whereas in cathodic protection, it's more of a empirical relation. Now, we'll try to look at some of the calculations related to current output from a sacrificial anode, as well as we also would like to see how to calculate a number of sacrificial anodes required for sending current required for a good amount of protection. As well as we also would like to see how to calculate the weight of the total anodes that will be required for giving protection to a structure for certain period of time. So, let's look at the calculation of current output. Now, if we look at the design of the setup for sacrificial anode protection. So, this is my, let us say, magnesium anode, and the current electron will flow this way and current will flow that way. This is current flow. This is let us say pipe which is getting protection. So, magnesium will dissolve and gradually will get protection. Now, when we try to do that, to understand that current output, that means this output current which is going into the pipe or leaving magnesium anode, that would depend on few aspects. One aspect is resistivity of soil. Second aspect, of course, this is rho, which is basically ohm centimeter, or it's ohm meter, whatever you would like to put it up. Now, geometry, generally long anodes give better current output. Or higher current output. And third is higher the driving potential, higher would be the now resistivity means I am talking about this soil. Now, this driving potential del V, you can consider the polarized potential for the part which is to be protected, and here it is OCP or open circuit potential of the anode. Now, if you connect it, that time the potential might vary a little bit, but if we initially consider the initial circuit potential, so that case if we consider anode pure magnesium, del V would be 1500 minus 850 millivolt, which is close to or 155. This is generally magnesium open circuit is 1.55 volt with reference to copper sulphate. So, these potentials in case of cathodic protection, generally copper sulphate reference electrode is used up, is actually used for measurement of potential, because that is a very rugged electrode, uh, and this reference electrode is very rugged, and it can be carried with hand, and it does not break easily. At the same time, when we try to measure soil resistivity, or when we try to measure the potential, polarized potential of the sacrificial anode, okay, or the pipeline. So, that time what we have to do, we have to connect the terminal between the pipe and that particular copper sulphate reference electrode. So, what we do, let us say in a place you have this pipe and this is the terminal. So, now in the soil, this is the soil, let us say in the soil I put that copper sulphate, I insert it into the soil very close to that material, that structure which is being protected by the sacrificial effect of another anode. So, we try to see this potential difference. Okay. So, that is what we need copper sulphate, and there as per NASA criteria is 850 millivolt in case of steel. So, if we maintain that potential or further down, so this potential polarized or E polarized, it should be less than minus 850 millivolts. So, further negative, and further negative means it is cathodic polarization. So, that is the potential we are talking about, and now when we try to see the potential difference between these two, so then it is nothing but this is minus 1550 millivolt, which is the OCP, and this is minus 850 millivolt. Now, when we talk about the potential difference between these two, which is the driving potential, that becomes 700 millivolt. Now, in case of zinc, if this becomes zinc, then del V is with respect to steel is around 250 millivolt. Fine. Now, these are the three aspects which would lead to higher current output. Now, basic equation is nothing but V equal to IR. So, now this increases, this remains same, then definitely I would increase. Now, if R decreases, V remains same, I would go up. So, this is one instance. Second instance is V go up, R fixed, I would go up. So, like that way we could see that resistivity and driving potential, they have direct relation with reference to this V equal to IR. That is a basic equation. Fine. Now, we can calculate that current requirement by using two formulas. In case of magnesium, when it is uncoated, because that current is given by magnesium, because this is sacrificial anode. So, we are not connecting it to any external power source. That has a formula like mg Img equal to 15000 Fy divided by rho. So, this is for uncoated magnesium electrode. So, now these values we can get it from different tables. To arrive at this equation, there are background calculations and all those equations are guiding that, but let us not get into those complications. Simplified way, we can put it like this, where f is a factor, y is also a factor, and rho is the resistivity. Fine. Now, so this is these are all decided by the anode weights as well as what is the kind of length and diameter those pipes. Those are the dimensions would decide what will be the factor f. This is, you can say, dimensional factor. Dimension as well as number of anodes to some extent. Now, y is nothing but it is related to pipe or tank which needs protection, and this with reference to soil. So, these potential difference would lead to different values of y. For that, definitely there are background calculations. We are not getting into those calculations. We are simplifying this particular equation. Now, if it is uncoated, this is the situation, and this is in terms of milliampere, that is the current you will get. Now, on the other hand, if it is coated, that time the current output, coated means this is the pipe I am talking about. When the pipe is uncoated, and here when the pipe is coated, so that time current output requirement would be less, and current output also becomes less. So, that means that time it becomes, the formula is 1,20,000 Fy divided by rho. Now, so in case of coated pipe, we do not require that much of current output, because let us say I have, this is a bare one and another one is, let us say, coated. If we make it coated, if it is coated, now by chance there is some sort of break in the coating, let us say this part is there is a break. Now, for protection we need to only send current here. Okay. So, that is what the current output becomes less. Now, in case of zinc as well as aluminum, we can find such equations. Now, we can calculate this current requirement using these formulas. Like one example, let us solve that example. Some data set, if we talk about. So, let us say we have what the problem statement says. Let us say we want to calculate current output for a 17-pound packaged magnesium anode. So, this would be helpful to find F from the table. Now, the resistivity of soil since this is the same arrangement what we have here. Okay, so resistivity of the soil, it's 2000 ohm centimeter, and the pipe, one pipe is being protected, so that is bare or uncoated. And the pipe and soil potential difference is around minus 850 millivolt. Okay, so that's the potential difference, and of course this is measured with respect to copper sulfate reference electrode. Fine. Now that case we can calculate. First let us see what is the F value. For that we can think of using this data set. Let us say standard anode, and this weight is in pound. Now details of the dimension as well as the arrangement. So if it is 3 standard anode we are using, and if it is packed or packaged, then we can use 5, then it is also packaged 5 number of course, then it is 9. Sorry, this is standard anode, this is a single anode. So this is 3, these are basically weight of single anode. So this is again packaged, and 17 pound, this is also packaged. Now if we try to see the factor F, so in this case it is 0.53, so this is 0.60, 0.71, and here it is 1.0. So F is equal to 1.0 from this table. So this table is much longer table. You can refer principles of corrosion engineering and corrosion control by Jaki Ahmed. So that book, if you follow in the cathodic protection segment, you can find these tables. On the other hand, you can also find out Y from the table. So here P by S, which is the pipe and soil soil potential difference. So that's, if it is minus 7.0, it can vary like 0.80, 0.85. These are in volt. Okay. Now for magnesium, it is 1.14, then it is 1.07, this becomes 1.0. For zinc, this is basically Y values. Zinc, it is 1.60, 1.20, here it is also 1. Fine. So this is Y, which is a correction factor actually, and it is dependent on resistivity of the soil. Now, and also the dimension. So this factor Y comes up, and also we know the resistivity value is already given. So we put those in that equation, and here since it's a bare, so we have to use IMG equal to 15000 Fy divided by rho. Now since it's a packaged magnesium anode, so F becomes Y. Y from the table we can find out, since the pipe to soil is 550 millivolt or 850 millivolt, and or 0.85 volt. So, Y is 1. Now, IMG equal to 15000 into 1 divided by 2000. So, it becomes 75 milliampere. So, that is the current output. Now, if we, and this is, remember, this is for single anode. Now, if we try to find out multiple anode, let us say if we try to find out multiple anodes, let us say we talk about 4 parallel anodes, and they are of 10 feet apart. One can obtain, so this current requirement becomes like this. IMG would become, now here also you have to use one correction factor. So, that correction factor comes from the number of anodes as well as anode spacing in feet. So, that case the formula is like this, correction factor depending on anode number and distance between two anodes. Okay. And then the current what one anode gives. So, this is the, so the current output by one anode. Now, here we can again use make use of a table. So, here it is number of anodes and adjusting factor or the correction factor. So, now we can think of this is coming because of number of anode and anode spacing. So, if we talk about 2 anodes, so number of anodes, let us say 2 number. Now, if it is 5 feet away, if it is 10 feet away, if it is 15 feet away, and then we can also think of 20 feet. So, that time these values becomes 1.839, 1.920, 946. So, like that way you can find out for different numbers of anodes. Now, we are considering 4 anodes, 4 number. So, these values for different anode spacing becomes like this, 3 point, if it is 4, when it is 3 feet away, 5 feet away, 0.036, 455, this is 65, this is 37.14 like this. So, now we have put 4 parallel anodes and 10 feet apart. So, we have to use this 4 number and then this table we have to use. So, this is the value we have to use. Now, in this equation we can put it 3.455 into, we have already calculated for magnesium with that condition, 75 milliampere. So, this becomes 259.125 milliampere. So, this is the total current output. This is total current output. It is basically multiplied by the 4 anodes. Only difference is if we consider only difference is that correction factor comes for different other reasons, because when you try to use the basic equation V equal to I R, that R contribution would be different at different segments and different junctions. For example, there could be one R due to the backfill and the anode, and then backfill and soil, and then soil and soil and pipe surface. All those resistance factors would come up. So, that is what it is not exactly the current that is given by one anode and multiplied by the number of 4 number of or a number of anodes what we think of using, and then find out the total current output. So, there should be a correction factor because of those variations in resistance and dimension, shapes, all those factors. So, we do not get into those complications. This is a simplified way of looking at it. Now, we can also calculate number of anodes by using simplistic formulas as well as weight of the anodes, total anodes for a specific period of protection. So, let us look into this. So, now another mode of calculation what we can think of is calculation of number of anodes required and what could be the spacings. Okay. So, in order to do that, we can also calculate, for example, let us see the problem. So, let us put up like this, think of a pipe which is to be protected, and this is bare, uncoated, and if we try to see the dimension, it is 1000 feet, and this is the length, cylindrical pipe, and the diameter is, let us say, 24 inch. So, this is diameter. Now, it is to be protected. Now, for that we need to send some amount of current density. So, let us say we need a constant supply of current density of 1 milliampere per feet square. Now, the resistance or resistivity of the or resistance, let us say resistance of the soil is which is R ohm per centimeter cube, let us say, and we need to for anode output, anode current output, let us say that value is around 100 milliampere, single current, single anode that has this particular, and this is specific to this type of soil. So, this is the current output. So, we can calculate number of anodes. So, first we have to find out the area and total current requirement. So, we have to calculate the number of anodes and spacing for this specific current density that is to be supplied to the pipe. Now, area of the pipe we can calculate 2 pi r h, 2 into 3.14 24 into 1000. So, this is 24 is basically the in inch. So, in order to convert into feet, so we divide it by 12, and this is the diameter, so we divide it by 2. So, this is feet square. So, this is the area, surface area. So, we can get rid of this. So, then it becomes 260. So, this is the total area, and we know what is the current that will be required for protection of the entire area. So, which is the current density required is equal to 1 milliampere per feet square. So, then total current that is to be required is 6280 into 1 equal to 6280 milliampere. Now, we know the anode current output. So, that has been calculated by using that formula. If it is a magnesium anode, so then it is 15000 Fy divided by rho. This is Img when pipe is bare. So, the magnesium is never coated. So, it is pipe that is coated, and coated case this value would become 120000. Now, those F and Y we can find out from those tables as we have discussed just before coming to this part. Now, this is the total current that will be required for protection when we need to supply this much current density. So, number of anodes in a simplistic simplified manner, we can calculate this total current output required by the pipe or by the pipe surface divided by current output of a single anode. So, here we are not using any correction factors for multiple anodes if they are put up at some distance. So, that case it will be 6280 divided by 100 milliampere. So, this should be the value. So, this comes around 62.8, which is roughly around 63 anodes. I remember when we use this formula, because this is this 100 milliampere, that current output is for a single anode. Now, if we use multiple anodes and if we put at a different distance, let us say 5 feet or 10 feet or 15 feet, there should be some correction factors, but roughly those correction factors can be taken as same as the number of anodes. So, the correction factor that can be taken, for example, if we use 4, the correction factor also becomes 4. So, like that way we can put it up, but here we are actually not using that specific correction factor. So, we are simply using that this much. If one single anode gives 100 milliampere current, so then the 63 anodes would give you the 63 into 100 milliampere, that is the total current required to meet this current density. So, this is the way to calculate number of anodes. Now, one can also calculate total weight of the anode. So, that would be calculated on the basis of let us say I want to supply 1 ampere current for let us say 10 years. So, 10 years protection would be required, and I know the capacity. This is the requirement for protection. So, 1 ampere current for 10 years, that will be requirement, and we know the anode capacity. So, now we know the magnesium has anode capacity of the order of 50% of its theoretical. Earlier we have also calculated, we have also seen how to calculate this theoretical anode capacity by using the atomic weight of that particular element, and then trying to see that element dissolves, and theoretically it should not have any self dissolution, that means self corrosion. For example, if we have a magnesium rod, whatever dissolution happens, and that particular dissolution, whatever current output it gives, that will be entirely used up by the pipe. So, that time we do not have any self dissolution, like for example, there could be local cells. So, local, this is positive, this is negative, that local cell forms. So, the current will flow from negative to positive, which is cathode, this is cathode, this is anode, and current will flow from negative to or the anode to cathode through the soil. So, this part will dissolve. So, that time we have self dissolution, but in theoretical situation all the cathodic reaction must happen on the pipeline, but that may not, that is not the that cannot be possible in actual situation. So, that is where the efficiency drops down. So, magnesium operates at 50% of its efficiency. Now, if we know the value of that anode capacity, let us say x, which gives in terms of ampere hour per kg. So, now we can find out what should be the weight by using this formula, current into specific period of protection. Here it is 10, and this current is nothing but 1 ampere. We are saying that 1 ampere current should flow, and then divided by the capacity, anode capacity, which is in terms of ampere hour per kg. Ampere hour per kg, and then we have to also multiply with one factor, say 8660, and this comes because whatever calculation we are doing in terms of, if we do not put this value, we are doing in terms of 1 hour basis. Okay. So, now we have to find out for 10 years how many hours it becomes. So, for 1 year we can calculate how many hours, 365 into 24, 365 days. So, this if we multiply, you should get this. So, that becomes the total weight. So, now if we, so this is total weight in terms of kg. So, 1 ampere into 10 into 8760 hour into kg ampere hour. So, this become this much kg. Now, this is done with respect to 1 ampere. So, this can vary. So, let us say I want 100 milliampere. So, you put that value, current value here. So, this is nothing but the current value that is required for 10 years for protection. So, if we put that, you can also find out what is the kg. You find out the number of anodes. Now, the basic formula becomes total weight in kg required for protection with the requirement of some specified amount of current output or current density you can think of, just like previous problem. So, that we can find out. Let us say we want this is let us say this is x is the current in ampere, let us say, y is the years of protection, anodic let us say z equal to anodic efficiency. This is practical, not theoretical, which is impossible to achieve. So, then we can put that formula, kg is equal to x y into 8760 divided by z, and this is in terms of ampere hour per kg. And in fact, if we look at this thing, we are just operating with the units, and that is what we are left with, kg. So, if you do that, this is in terms of kg, you will get it. So, these are some of the calculations which we can use for designing anode numbers, as well as or finding anode numbers, or what could be the current output, as well as weight of the anodes required for specified period of protection to a structure. There are lot more calculations that can be done. So, let us not get into those complications. These are all very simplified situations I am talking about. So, let us end this discussion, and from the next lecture onwards, we will start talking about inhibitors. So, till then, thank you.